Okay, so for the Chapter 3 and 4 test review, I'm going to start with the Chapter 3 problems. So this is reviewing sampling methods, observational studies and experiments, and then bias. So in the first question, it says a student at a large university wants to study the responses that students receive when calling an academic department for information. She plans to randomly select 6 departments and sample all of their students. So anytime you are grouping people for a sampling method, it's either going to be stratified or cluster. The difference between the two is whether or not you're sampling people from every group or a certain number of groups and everything within those. So because she's selecting 6 departments and sampling all of their students, this is cluster sampling. If she were selecting a specific number of students from each department, then it would be stratified. So using the same thing, we are now going to figure out which 6 departments are going to be part of her study. So we have a line from the random number table and we have the list of our departments. So the first thing you need to do is number all the departments. And because there are more than 10, every department is going to get a 2-digit number. So 0, 1, and because it's alphabetical, it does work better if you just go ahead and keep the order alphabetically and number them that way. Now, my numbers from the random number table, I need to split up into 2-digit numbers. So after every 2 numbers, I'm going to draw a vertical line, and that splits it up into my 2 digits. Okay, now I only want to select numbers that are within my range, so between 1 and 27, and I don't want to repeat any. So my first 2-digit number is 14, which is within my range. So the history department will be included. Then 45, 92, 60, 56, 31, 42, 48, all outside my range. My next one was 3, so the art department. Then 10, the education department. 22, the philosophy department. 6, the chemistry department, and then 11, the engineering department. Now, obviously, if the 6 departments hadn't been all in the first line, I would have needed to continue to the next line to make sure that I include 6. All right, now what we're going to do is we have 6 different sampling examples, and we're going to determine which sampling technique was used. So cluster, convenience, simple random, or SRS, because we typically do abbreviate it SRS, stratified, systematic, or voluntary response. So the first one says you survey every 5th person leaving a movie theater. So anytime it mentions every eighth number of people, so every 3rd person, every 5th person, every 22nd person, whatever, that is always systematic. The next one says you survey every person who attended the 7 o'clock showing of Avengers Endgame. So every showing of a movie can be considered a different group. So we're selecting one showtime and surveying everyone at that showtime. So this would be an example of stratified. Sorry, cluster. We selected one specific showing and everyone within that. So that would be cluster. If we select 5 people from each showing, so again, each showing is a different group, we've selected a specific number from each of those groups, this is stratified. Next, we have that you survey your friends who went to see Avengers Endgame. So this would be convenience. The next one says each person who sees Avengers Endgame is assigned a number, and you randomly select numbers to determine who is surveyed. So because every person has an equal chance of being selected, this is the SRS, the simple random sampling. And the last one says everyone who purchased a movie ticket for a specific date was sent an email with a survey to complete about their experience. So this is voluntary response. The other one that gets commonly confused are convenience and voluntary response, because a lot of people, voluntary response is a convenient way. The key difference for us is who is it convenient for? The person doing the surveying or the person being surveyed? So if it's the person doing the survey, it's convenience. If it's the people completing the survey, it's voluntary response. So for them, they don't really have to go out of their way to do the survey. They can ignore it, pretend it doesn't exist. So that's the key difference between voluntary response and convenience. Next thing we're going to take a look at is observational studies and experiments. So knowing the difference between an observational study and experiment. So for an observational study, you are either using data that already exists or you are asking people to report on their behavior without changing anything. So, key part of it, you're observing your subjects without changing behavior. Whereas an experiment, you are imposing a treatment or treatments on a group of subjects. And it can be multiple treatments. It doesn't just have to be one. So the next thing is we're going to look at an example. So in order to test whether a new drug relieves migraines faster, a group of 2,500 adults aged 25 to 40 is selected. They're randomly assigned to 4 groups. Group 1 receives the new drug. Group 2 receives Excedrin. Group 3 receives Motrin, and Group 4 receives a placebo. The adults rate their pain on a 100-point scale before and after taking the medication. So the first thing is this an observational study or an experiment? And because you are assigning people to groups and telling them which drug to take, it is an experiment. If you had asked the subjects to just take whatever pain medication they currently take and then rate their pain before and after taking it, that would be an observational study because you're not asking them to change something that they would normally do. But it doesn't really help when you're trying to test a new drug. Anytime you're trying to test something new, you typically have to do that through an experiment. The next thing we want to do is to identify the explanatory and response variables. So the explanatory variable does have to be the thing that you are controlling or in the experiment. So in this case, our explanatory variable is the medication. And then the response is going to be the outcome, which is the pain rating. Now we want to construct a design of the study. You can construct a design using words. It can just be like a paragraph explaining how you would do the experiment. Another easy kind of way to do it is to do a tree diagram, which I think is a little bit easier, but it's personal preference. So either way, you have to start with your your sample. So we start with our 2,500 adults, which they're going to be in one of 4 groups. So we have group 1, which is the new drug. Group 2, group 3, and group 4. So all of my groups were already defined, so I don't need to rewrite them out. You can if you want. Because, and this is important, we know how many people are in our sample, we then also have to indicate how many of them are going to be in each group. So 2,500 divided by 4 is 625. So there are 625 people in each of our groups. We also have to indicate how randomization is playing a role. And in this case, we are randomly assigning our adults to each of our 4 groups. So RA here indicates the random assignment. And then at the end, we would then just say all 4 of these come together and we're going to compare the results. And like I said, you can do this with words, like as a paragraph response. It doesn't have to be the Venn diagram. Okay. The rest of the problems are reviewing chapter 4. So we have the probability that a high schooler has a phone is 0.96, and we want to figure out the probability that a high schooler does not have a phone. So the probability something not happening is 1 minus the probability it does. So in this case, this should be 1 minus 0.96, which gives us 0.04. The probability that 2 randomly selected high schoolers have phones, so these are independent events, which means the probability is just multiplying each together. So 0.96 times 0.96, which is 0.9216. The next 2 problems go together. So we have a bag of candy that has 11 green, 9 orange, 9 blue, 8 red, 7 yellow, and 6 brown M&Ms. We are selecting an M&M. We want to find the probability that's red. So the probability it's red is the total number of red M&Ms, 8, over the total in the bag, which is 50. And the way I got that is just adding all of them together. So the total is 11 plus 9 plus 9 plus 8 plus 7 plus 6. Give us 50. If you want with these fractions, you can leave it as 8 over 50. You can also simplify it. So 4 over 25. You can also write it as a decimal. This is an exact decimal of 0.16. Typically, I would say at least 3 decimal places for probability, but when it's an exact, you can just give me the exact. The next one says the probability that it is green or yellow. So anytime you have an or probability, you add each individual event and then you subtract their overlap. So green, there are 11 out of 50. Plus yellow, which there are 7 out of 50. Now in this case, there is no overlap. I cannot select an M&M and have it be green and yellow, so my answer would just be 18 out of 50, which becomes 9 over 25, or 0.36. And the last one says the probability it's not orange. So similar to the first problem, The probability that something is not orange is 1 minus the probability it is orange. So that would be 1 minus 9 over 50. So 50 minus 9, which give us 41 out of 50, which is 0.82. So now we're using the same bag of M&Ms, but now we're selecting 2 pieces of candy and we're not replacing it after the first draw. So we want to find the probability that the first M&M is brown and then the second is blue. So probability of brown, then blue. So the first probability is not affected by the without replacement. So we're going to have 6 out of 50. And this would technically be and, so we are multiplying. My second probability is then affected. So there are no longer 50 M&Ms. There are only 49. And then there are 9 blue. So then 6 times 9 is 54 over 50 times 49, which is 2450, which you do not have to simplify that large of a fraction. You can just leave it as a decimal, which is 0.022 and then 0, so 3 decimals. Okay. The next one is the probability that both are green. So it's green and green. So the probability that the first one is green is 11 out of 50. Similar to the previous example, my denominator has to decrease because there's no longer 50. In this case, my numerator is also going to decrease because it's 2 green in a row. So there's no longer going to be 11 green after I choose the first one. So then we get 110 over 2450. Which is 0.0449. And the last one says the probability you do green, then red. So the probability that the first one is green is 11 out of 50, and then times red, so denominator is still going to become 49, and then there are 8 red. So it becomes 88 over 2450, which is 0.0359. The next problem, we have a table of information about DACC students and if they drive to school and then whether they are half day or full day. So we're now going to find probabilities associated with that. So the first probability we want to know is if a student is selected at random, the probability that the student drives. So that means we care about the row of students who drive. So probability a student drives is going to be 225 over 600, which is just 0.375. Next, we want to find the probability that a student drives given they are a full-day student. So remember, whatever comes after the word given is the row or column you are restricting your total to. So we are restricting this to the number of full-day students, and we're specifically saying of those full-day students, how many of them drive. So my answer is going to be 115 over 400. Which is going to be 0.2875. The next one says the student doesn't drive or is a full-day student. So we have doesn't drive, and we say or a full-day student, but then we want to subtract the overlap because we don't want to count those students twice. So we start with 375 over 600 plus the 400 over 600, and then we're going to subtract 285 over 400. Another kind of key, 285 over 600. Another key piece of data that let you know that you have to subtract is if I did 375 plus 400, I'm going to get 775, which is over 600, which would mean you have a probability greater than 1. And you can't ever have probabilities greater than 1. So the answer ends up being 490 over 600, which is 0.8167. The last one says, are the events, drives, and full day independent? So to check if two events are independent, you want to check if the probability of A equals the probability of A given B. So we'll define drives as A and full day as B. So the probability of A is the probability a student drives, which we calculated already as 0.375. The probability of A given B, so the probability a student drives given their full day student, we calculated already, and it is 0.2875. And because those probabilities are not equal, the events are dependent. So the events are dependent. And then it would be because 0.375 does not equal 0.2875. Next one is an example of combinations. So we have an Algebra 2 class made up of 10 females and 6 males. A group of 7 students is being put together for a project. We want to know how many total outcomes are there for selecting the 7 students. So we first have to find the total number of students, of which there are 16. So of those 16, we are choosing 7. If you want to do the factorial, it would be 16 factorial over 7 factorial, 9 factorial. You're not required to do the factorial. You can use the combinations in the calculator. But it ends up being 11,440. Now, the probability of selecting a group that is specifically 5 females and 2 males, we have to do 2 combinations in the numerator. So of the 10 females, we are choosing 5 of them. You then multiply it by, of the 6 males, choosing 2 of them. And then it's still over the 16 choose 7. So when I do 10 choose 5, you get 252 times the 6 choose 2, which is 15, over the 11,440, which you can leave as 3,780 over 11,440, or you can write it as a decimal, 0.3304. Both are very acceptable. I don't care which you do. Next, we are doing a group of 7 females. So all of the members of the group are female, no males. So our numerator is just 10 choose 7. And then our denominator is still 16 choose 7. So our numerator, we just get 120 over 11,440, which is 0.0105. And the last one is 5 males and 2 females. So we do 10 choose 2 for the females times 6 choose 5 for the males over the 16 choose 7. So we do 45 times 6 over the 11,440, which becomes 270 over 11,440. Which is also 0.0236. Next one is a different type of combination problem with the lottery. So your parents play the Powerball each week, which consists of selecting 5 numbers between 1 and 69 and 1 number between 1 and 26. And then we have 2-digit numbers that cannot be repeated. So we want to know how many different combinations are there for a winning lottery ticket. So the numbers between 1 and 69, there are 68 of them. 69 of them. sorry, there's 69 numbers between 1 and 69. So we are choosing 5 of them. So we're going to do 69, choose 5 times, and then the numbers between 1 and 26, there are 26 of them, and we're choosing 1 of them. So if you do 69, choose 5, you're going to get 1, 1, 2, 3, 8, 5, 1, 3. And then 26, choose 1 is going to be 26, choose 1 is 26. When you multiply the two numbers together, you're going to get 2922091338. And then the probability that you win the lottery, there's only one winning ticket, so it's just 1 over the different combinations. And then you're not going to want to write that as a decimal because it ends up being a very, very small decimal with scientific notation. Next one we have that at a fundraiser, they're selling 1,000 raffle tickets for $3 each. The prizes are a TV valued at $600, a new iPhone valued at $1,200, a cash prize of $250, and 10 Starbucks gift cards valued at $20. We want to construct the probability distribution table. So my variable X is going to represent the winnings. And you have to remember that from the winnings, you have to subtract the cost of the lottery ticket. So the $600 prize becomes $597. $1,200 becomes $1,197. $250 becomes $247. And then $20 becomes $17. And then because you are also not guaranteed to win anything, you have to have the -3 for if you lose. Then the probability is how many of the tickets are there for that prize. So there's 1 out of the 1,000 for the TV, 1 out of 1,000 for the iPhone, 1 cash prize, 10 out of the 1,000, and then the remaining are losing. So 1 plus 1 plus 1 plus 10 is 13. So that means 987 out of 1,000 are going to be losing losing raffle tickets. They're not going to win anything. So then the expected value of a raffle ticket will then determine whether or not we should buy a raffle ticket. So to get our expected value, we take each outcome and we multiply it by its probability and we add them all together. And when you get to the last one, the plus -3, you can just do it as -3 in the calculator. You don't have to do plus and negative. So you type this all in a calculator. You can do each of them separately and then add them all together. I recommend just doing it all as one line in the calculator. And because it is price, the expected outcome will be money. And it ends up being -75 cents. So this tells me, because my outcome is negative, that I shouldn't play the game, or you shouldn't buy a raffle ticket, because you are expected to lose. You're not going to lose a lot of money, but you are still going to lose, and anytime you're going to lose, I always recommend not doing it. So the next one says, in your closet you have 6 pairs of jeans, 4 pairs of shoes, 8 sweatshirts, and 11 t-shirts. How many different outfits are available if you select 1 pair of jeans, 1 pair of shoes, 1 sweatshirt, and 1 t-shirt? So you're just multiplying all together. So 6 times 4 times 8 times 11, which is 2,112. The last two problems are the binomial and geometric problems. So when you're trying to decide between the two, you are trying to figure out, am I given a sample size? If so, it's binomial. If you are doing something until a first success happens, then it's geometric. So in this first problem, we have a dentist performs root canals 8 times in 1 month. There is a 95% success rate. So because we're talking about doing something a specific number of times, it is binomial. So we want to find the probability that all 8 root canals are successful. So that's the probability that x equals 8 anytime it's an exact. So all or exactly, like 6 or whatever. You have to use the formula itself. So that would be h choose 8 times 0.95 to the 8th, and then times 1 minus 0.95 to the 0. Which in this case, because you're saying all 8, you could just do 0.95 to the 8th. It ends up being the same way. But if this had supposedly said the probability that 6 out of 8, then we would have had 8 choose 6 times 0.95 to the 6th, and then 1 minus 0.95 squared. So you end up with 0.6634, which is not a bad probability comparatively speaking. All right. The next one is an example of a CDF. So we want to find the probability that more than 5 root canals are successful. So this is the probability that x is greater than 5. Anytime you have a inequality for binomial distribution or even geometric, you have to rewrite it so that it is a less than or equal to, because the binomial CDF and the geomet CDF in the calculator will only do less than or equal to. So everything that's not greater than 5 is 1 minus everything that's less than or equal to 4. Sorry, less than or equal to 5. So in this one, it's a little bit different. I don't have to subtract 1 from the 5 because it doesn't have an equal to. You only have to change the number if it's a greater than or equal to. So we're going to do 1 minus binom CDF, and then we're going to have 8.95 and then 5. Yeah. So that's going to be 0.9942. The next one says find the mean number of successful root canals. So that's our E of x, which for a binomial distribution is just n, which in this case is 8, times p, which is 0.95, which is going to be 7.6. And then for the standard deviation, that is the square root of n, which is 8, times p, which is 0.95, and then 1 minus p, which is 1 minus 0.95, which is 0.6164. The last problem is going to be geometric. So we have that there's a 38% chance of being nearsighted. So I haven't given you sample size. So that is the first kind of indicator that it's geometric. The second one is that we're asking about how many times you'll have to do something until you get the first. So what is the probability that the 5th person you survey is nearsighted? So it's basically saying, what's the probability that you have to ask 5 people before you find the first person who is nearsighted? So because it's geometric, it's the probability that y equals 5. So you start with the probability of failure, which is 1 minus 0.38, and then it's how many failed attempts you've done, which in this case would be 4, times your 1 case of success, which is 0.38, and that is 0.0562. Okay. The next one says, what's the probability that the 9th person you survey is nearsighted? So the probability that y equals 9. So 1 minus 0.38, and then we would have had 8 failures, and then our 1 success, which is 0.0083. The next one says, what's the probability that the first person who is nearsighted is within the first free survey? So this is an example of an inequality. So we have the probability that y is less than or equal to 3 because it says within the first 3 surveyed. So we're going to do 1 minus, and then we'll do Geomet CDF. And then we have our probability, 0.38, and then 3. And then it is going to be 0.7617. So you don't actually have to change anything on this problem. I don't know why I put 1 minus. You don't need the 1 minus. It's just Geomet CDF because it's already less than or equal to. You only have to do 1 minus if it's a greater than or greater than or equal to. And then how many people would you expect to survey before finding someone who is nearsighted? So E of y for the expected outcome for a geometric is just 1 over your probability. So in this case, that's 1 over 0.38, which is going to be 2.63. So let me know if you have any other questions about Chapter 3 or Chapter 4.